Welcome to the second part of our branches mnemonics overview. This time we're going to talk about the instructions that are marked in bold. These instructions are called skips, and they are conditional and restricted jumps. The difference is that these skips are conditional. They don't always jump. The branches are also conditional, however they are much less restricted jumps, and we'll see them on this video. So the first instruction we're going to cover is skip if bit in register is clear. So here we have the following code. At address 0 we have stored the skip if bit in register is cleared. In address 1 we have relative call, and in address number 2 we have a NOT operation. So register 0 has 8 bits. This bit can be 0 or 1. So depending on the value of this bit, this instruction is going to jump the next instruction. If here we have a 1, then we're not going to jump this instruction. We are actually going to execute it. However, if we have a 0 here, the instruction, in this case the instruction is a relative call, this instruction is going to be skipped. So we're not going to execute it if this particular bit is a 0. Now let's take a look at the following code. It's very similar, with the difference that the next instruction is a call. The call, as you know, takes 2 places in the flash memory to be stored. The difference here is that if the first code skips, it's going to jump from address 0 to address 2. And in the second code, if this instruction skips, it's going to jump from address 0 to address 3. This because the call mnemonic takes 2 places. If the bit that we want to read is 0, the program counter, it's going to be the program counter plus either 2 spaces or 3 spaces, depending on the following mnemonic. Otherwise, the program counter is going to be the program counter plus 1. An important thing to notice is that this knob here and also the knob at the left are always going to execute. The instruction that it's conditional, it's the one that it's after the skip. This instruction, it's the one that either it's going to be executed or it's going to be jumped, depending on the status of a bit. The next instruction is skip if the bit in a register is set. In the following example, you can see we're checking bit number 4 in register 0, and if this bit is 1, if bit 4 at register 0 is 1, then it's going to jump to this instruction. If this is 0, it is going to execute this instruction. We have the same operation, both access all the 32 general purpose register, and the number of cycles, it's very particular. You have 1 cycle if there is no skip, so if the condition is false, it takes 2 cycles if this instruction skips 1 word or 1 location in flash memory, which is the case of this code. And it's going to take 3 cycles if the next instruction is a 2-word instruction, which is the case of this code. This code here is going to take either 1 or 2 cycles, and this code here it's going to take either 1 cycle if there is no skip, or 3 cycles if there is a skip. This instruction is going to take either 1 if there is no skip, or since we have a call here, we're going to have either 3 cycles. Next, we're going to see a very similar mnemonic. However, this mnemonic skips if a bit in an IO register is cleared or set. To check if it is cleared and skip if it is cleared, we have the mnemonic SBIC, and if we want to check if a bit is set, we have SBIS. Here we have an example. In this case, we have pin Z, which is an input-output register, and if bit number 1 of this particular register is cleared, that means if this bit is 0, then the multiplication it's not going to be executed. This instruction can only access the lower half of the 64 input-output register, and the cycles are exactly the same as the previous instructions. Now let's talk about the comparison mnemonics. They're just a preparation for branches. So the only thing a comparison does is that it modifies the flags in the status register. The only thing a branch does is make a conditional jump depending on the status of these flags. Basically, a comparison is mostly useless without a branch because it does nothing except changing flags. However, branches can be used without a comparison mnemonic, as long as you make sure that the correct flags, the flags that you need obviously, are modified before the branch. This can be done with an arithmetic operation because if you remember, arithmetic operations modify flags. So let's see the first mnemonic, which is compare. This mnemonic performs a comparison of two registers. This comparison is done through a subtraction, which is very similar to the sub mnemonic. However, the difference with the sub-mnemonic is that this instruction does not change any register. All this instruction does, again, it's modify the status register. So here we are loading a 100 to register 16. And let's see what 100 is in binary. So 100 in binary is 0110, 0100. This is the most significant bit, and this bit is 0. So it has the same value if it is considered unsigned or signed. In the next line we have load the immediate constant 200. And with 200 we have the following. This is the number 200 in binary, and as you can see, if we consider this unsigned, well, this value is 100. However, if we consider this signed, this is telling us that we have a negative number. And in order to know which value this is, we can perform the 2's complement to get the absolute value of this number. And if you make this, you should have 56. You can do this if you want to check that this number is minus 56. Next, we have compare register 16, register 17. Now here, a very important part, the order matters. It's not the same to compare register 16, register 17 than doing the opposite. It is not the same if you compare register 17, register 16. The order really matters in this operation. And as you can see in the comments, this operation will perform a 100 minus 200. Of course, this is if we have register 16, register 17. If we change this to register 17, register 16, then we have 200 minus 100. However, you're seeing in the comments that it says or, we're going to have 100 minus 56. Again, remember, this instruction performs a subtraction. So we're going to subtract either with sign and without sign. And actually, we're going to do both. So what happens with the flags? Here I have written the flags, which is the half carry, the sign, the 2's complement overflow, which is the V, the negative flag, the zeta flag, and the carry flag. And I'm going to write with the value of these flags as we perform this operation. First, let's start with the easiest one, which is the carry. The carry, it's always going to be 1 if the second operand, which in this case it's register 17, it's greater than register 16 in this case. You're going to consider that you're performing 100 minus 200. So in this particular case, since register 17 is greater than register 16, the carry is going to be 1. Next, we're going to talk about the next easiest, or maybe this one is easier actually, which is the zeta flag. The zeta flag in this case, it's very easy. The zeta flag, it's if the result is 0, then the zeta flag is going to be on. So of course, 100 minus 200 or even 100 minus 56, both operations are not 0. Then the zeta flag is going to be 0. For the following 4 flags, we actually need to perform the operation. So what I'm going to do is I'm going to perform 100 minus 200, and I'm going to see how these flags behave in the process. So here we have the binary values of 100 and with the binary value of 200. And we're going to start subtracting these values. You could perform the 2's complement of 200 in order to get, let's say, the negative value. However, in this case, we're gonna go with the with the subtraction, especially because we want to know the half carry. So what is the result of this operation? First we start from right to left. So 0 minus 0, of course this is an easy one. 0 minus 0 is 0. Then we go to the next column, and 0 minus 0, it's also 0. Next we have 1 minus 0, and this is also easy. 1 minus 0, of course, it's 1. Next we have 0 minus 1. So 0 minus 1, it's negative 1. And what I have to do is borrow from the next bit. However, the next bit it's also 0. So we have to borrow from the next bit. And for that I'm going to cross this 1. And this one is going to become a 0. Okay, and this is going to borrow to the next bit. So this one is going to become a 1 0. I'm going to put it here because I'm borrowing to the next place. However, since I need to borrow another from this number, or from to the next column, this 1 0, which is a 2, if you subtract 1, this is actually going to become a 1. Okay, so I also cross this, and this becomes a 1. Okay, because I borrow to the next column, and this becomes 1 0. This column becomes 1 0. So now I have 2 minus 1. Okay, this is the way we read it in decimal, and 2 minus 1 is going to give us 1. Since we borrowed from this place to this place, so we had a borrow here, this is the half carry. We had a carry, okay, which in this case is a, let's say, a half borrow. So in this particular case, because of this, the half carry becomes 1. Continuing with the example, next we have 1 minus 0, and it is going to be 1. Then we have 0 minus 0, and we're going to have a 0 here. Next we have 1 minus 1, and of course 1 minus 1 is going to be 0. And then we have 0 minus 1. What happens is we're going to borrow from the carry. We're going to assume that the carry is 1. And actually, this is another reason why this flag here is 1. So we borrow from the carry to this bit, and this bit becomes 1 0. Okay, so since we have 1 0, it would be 2 minus 1, and 2 minus 1, and 2 minus 1 would be 1. So now we have the next status flag. This one here, and remember the most significant bit from this operation is going to be the N flag. So the N flag is going to be a 1. This warns me that the number can be negative. The next two flags are very, very important. In this case, for these two remaining flags, we're actually going to pay attention to this here. If we consider these two numbers to be with sign, we're having 100 minus 56. So this result, I'm not gonna go with the binary operation. I'm just gonna go with the decimal operation. So 100 minus 56 would be equal to 156. This would be the result. However, if you consider an 8-bit number with sign, you know that the limits of this number are from minus 128, this is the most negative value you can have in 8 bits, to 127, this is the most positive value that you can have with 8 bits. So since this is a range we can have in an 8-bit value, and since the result is greater than the upper limit, which is 127, this is what we consider a 2's complement overflow. And because of that, the microcontroller is going to tell me the V flag is going to be 1. The way to read this is that the value does not fit in an 8-bit signed number. And this is going to be interesting. If you remember the result, we have to remember just the N flag. So this means that the most significant bit was 1. So this means, okay, be careful, this can be negative. However, you can see that if you consider both operands to be with sign, you're actually seeing that the operation is positive. So even if the 8-bit tells me that we can have a negative number, we are also having an overflow of 2's complement. And if you remember, the sign bit, it's equal to the XOR between the V flag and the negative flag. This means that if both flags are equal, the sign bit is going to be 0, which is the case in this example. We have v equals 1, n equals 1, so the s flag is going to be 0. After executing this instruction, those flags are going to be on the status register. If we consider these numbers to be without sign, then we need to read this flag, because 100 minus 200, it's actually negative. However, if we consider these numbers to be with sign, then we have to read this flag. And this flag is telling me, oh, the result is actually positive. This, it's basically a decision of what those numbers actually mean for your program. The operation is very simple. It's a subtraction. Again, remember, this does not modify. In this case, this does not modify register 16. And this instruction can address all 32 general purpose registers. Now let's see similar mnemonics. They do practically the same. I'm not going to go through the whole explanation of why the flags are like that. We have the next example. We have register 16 to be 100, register 17 to be 99, and then we have an instruction which turns on the carry, which is SEZ. Then we're going to compare register 16, register 17. It is going to compare register, or it's going to subtract register 16, minus, and this is going to be register 17 plus 1. This is for this particular example, okay? The correct way to put this as a general formula, it's register 17 plus the carry, okay? So the carry can be 0, okay? So be careful. In this particular example, since we have this instruction, then this instruction is turning on the carry, so we know that a 1 is added to the register 17 before comparing it to register 16. So since this operation performs 100 minus 99 minus 1, the result is 0. However, take a very close look. The zeta flag is going to be 0. Even if the result is 0, remember, if the result is 0, we say that the zeta flag turns on. The zeta flag is going to remain unchanged if the result is 0. It doesn't say zeta flag is going to be 0 if the result is 0. It doesn't say zeta flag is going to be 1 if the result is 0. It says whatever the value of the zeta flag that was before this operation, if the result is 0, the zeta flag is going to remain unchanged. And this instruction can access all 32 general purpose registers. Now, the next instruction is compare with immediate. This instruction compares one register to a constant. Here we're loading -1 to register 16. Okay, so register 16, we know it's -1, and then we have compare with immediate register 16, 255. This is going to compare register 16, okay, minus a constant. So this operation, what it does, is going to say, okay, I'm going to compare -1 and I'm going to subtract 255. Okay, this is what you would think this instruction would do. However, you have to be very careful. -1, if you have the value -1, this -1 is actually 255. So this actually will do 255 minus 255. Because of this, all the flags are going to be 0, but the zeta flag. The zeta flag is going to be on because the result is 0. This particular instruction can only access from register 16 to register 31. And this is the final compare mnemonic, which is compare and skip if equal. And this is a comparison and a skip combined in one instruction. This is very similar to the following pseudocode. If x is different than y, then perform an operation. This is tricky. Be careful, because the mnemonic says compare and skip if equal. So you would think that the code would be something like if x equal to y, because you're saying skip if equal. You have the word equal. So you would say, okay, this is more like if they are equal, then make an operation. The correct way is that it compares to registers, and if it is equal, it skips the next instruction. So the instruction is not executed if they're equal. It's actually executed when they're different. If they're different, the next instruction is going to be executed. Okay, so be very careful. And this example says, okay, I'm going to start incrementing register 31, and then I'm going to start comparing these two registers. So I have register 0 and I have register 31. Let's assume that register 31 starts at 254. Okay, so this is the value of register 31 in the first iteration. And let's suppose that register 0 is 0. Okay, so let's assume these are the values, the initial values of this code. So at first we execute this instruction, and this instruction tells me increment register 31. So this instruction is going to make 255 register 31. Of course, register 0 remains unchanged. We don't have any instruction that modifies register 0. And then we come to this instruction. And this instruction says, okay, compare if both registers are equal. And if they are equal, skip. If they're different, don't skip. So the question is, it's 255 equal to 0? Of course not. They're different. So since they're different, this is not going to perform an skip. So if we don't perform an skip, we go to the next instruction, and the next instruction says, okay, go back. We're going to increment register 31 again, and since we have an 8-bit register, 255 is the maximum value register 31 can have, so this is going to become 0, okay, in the next iteration. And in this next iteration, of course, we're going to get again to the compare for the second time, and now it's going to ask, okay, are register 31 and register 0 equal? And of course they're equal. And since they're equal, I'm going to perform an skip. So the skip is going to skip the jump, and it's going to perform this instruction. So this will always be 0, because the only way we get to this piece of code, which is the subtraction, it's if both registers are equal. And if both registers are equal, then the subtraction is always going to be 0. This instruction can address all 32 general purpose registers, and similar to skips, it can be either 1 cycle, 2 cycle, or 3 cycles, depending on whether it skips or not, and the size of the next instruction. Okay, now let's see branches. Yeah, we have a lot of mnemonics, but you will see there's a little difference between them. And remember, branches are conditional, but less restricted jumps than skips. The restriction of skips is that they can only jump the next instruction, and branches do not have that much of a restriction. So the previous mnemonics, which of course were all the comparisons, were only a preparation for the following set of mnemonics. Remember, the only thing a comparison does is that it modifies the flags in the status register. And the only thing a branch does is make a conditional jump depending on the status of these flags. All branches are very similar. They do a jump-like instruction, but the jump is conditioned by a specific flag. Because of this, we will only see two branches, or we will only see two examples of branches, which are branch if equal and branch if not equal, but all the remaining branches are very similar. Only the flag or flags they check change, and some mnemonics even have the same opcode. So let's start with branch if equal. This instruction checks the zeta flag and jumps to the specified relative address if zeta is 1. It is called branch if equal because if you compare two equal numbers, the compare will perform a subtraction. Let's suppose you compare 20 and 20, and if you compare 20 and 20, you're going to do 20 minus 20, and the result is going to be 0. So if they're equal, the zeta flag is going to be on. So when you say branch if equal, what the instruction is doing, it's going to check the zeta flag to see if the comparison turned on the zeta flag. Here's an example. We have a comparison of register 10 and register 20, and then we have branch if equal. And we're saying branch if equal, and we're jumping to a label that says they're equal. Then we have some knobs. So first, the comparison, remember, the comparison is going to say, okay, register 10 minus register 20 without modifying register 10. If zeta is turned on, then it means that both registers are the same. And if they are the same, this instruction is going to jump to this knob. So these two instructions, if register 10 is equal to register 20, this is not going to execute. Or another way to see it is that if they're different, okay, if they're different, then these two instructions are going to be executed. If you remember, the skips could only jump one instruction. And in this case, we have two instructions. We're jumping two instructions, and we can jump even more instructions. Now, one thing that you have to be very careful is that one thing that you make a mistake usually, it's to think that if register 10 is equal to register 20, then this instruction is going to be executed. Okay, this is correct. If they're equal, this instruction it's going to be executed. However, if they're different, this instruction it's also going to be executed. The reason why it's because if they're different, we're gonna go to this knob, and then we're gonna go to this knob, and then eventually we will reach to this operation. This is much less restricted than skips. However, there's still a restriction, and the restriction is that we have 128 instructions, or in this case locations, that we can skip, and this means that we can jump from -63 to +64, and this is because of the constant. In this particular example, branch if equal and then label they're equal, this is as if we write 2, and that's because if we make a 2, then the operation is going to be 2 plus 1. Okay, it's going to be program counter equals program counter plus k plus 1. If you have doubts about this, I recommend that you go back to the jump instructions to understand this. The cycles of these operations are somewhat similar to the skips. However, we only have two possibilities. So it's going to take one cycle if the condition is false. It means that if it does not perform the jump, it's going to take one cycle, or it is going to take two cycles if it actually jumps. In this case, if zeta is 1, the condition is going to be true. Now let's see the opposite mnemonic, which is branch if not equal. In this instruction, if the previous instruction checked if zeta is 1, this instruction checks if zeta is 0. And jumps, of course, if this condition is true. This instruction is called branch if not equal because, again, a comparison is performed between two different numbers, and if they're different, then zeta is going to be 0. This is a better example than the previous one. We're comparing register 10 again and register 20, and we have branch if not equal, different, and what this is going to say, okay, I'm going to compare register 10 with register 20. If they're different, that's why it says branch if not equal. So if they're not equal, they're different, of course. So if they're different, we're going to skip to this instruction. If they're equal, that means that we're not going to jump. So we're going to go to the next instruction. However, take a close look. After executing this instruction, we have a relative jump. So this relative jump, it's always going to jump to this one here. So if the registers are different, then we're going to execute this instruction. Okay, this is going to be executed if register 10 is different to register 20. And this instruction here, it's only going to execute if register 10 is equal to register 20. So this code is very similar to the if-else code. And we have the same restrictions as the previous example. We have from -63 to +64 from the current program counter, and we have also the same cycles. What happens with all the 20 mnemonics? Well, all the 20 mnemonics work pretty much the same. They check one condition, they check if the condition is true or false, and if the condition is true, it jumps, and if the condition is false, it does not jump. Here we have a summary, and the summary is pretty easy to read. In order to better understand this, I'm gonna blank this part of this slide. You're gonna see that you have a lot of ways to perform comparisons, and if you want to make comparisons, all you have to do is first take a close look at the test column, and if you have the available comparison, then you can use the mnemonic, which is the third column. For instance, if you see on the second row, it says if register D is greater or equal than register right, then you should use branch if greater. However, first you have to look at the last column, which is the comment column. It says that the first 5 tests are for signed numbers. The next 5 tests are for unsigned numbers, and the final 4 tests, they're simple comparisons. Another important part to look at this summary is this note here. This tells me that we should interchange both registers if the operation or if we want to perform this specific operation. The reason why it's because we have a comparison that does not exist on the microcontroller, and this will be better understood with an example. Suppose we have 2 signed numbers and we want to implement the following pseudocode. The pseudocode says that if number 1 is greater than number 2, then we're going to perform an operation which is abs, which is another variable. It's going to be equal to number 1 minus number 2. Else we are going to say that the absolute value is going to be number 2 minus number 1. So first we go back to the previous slide, but right now I just put it here. Let's see what we're being asked. If one number is greater to another number. Okay, I want to check if register D is greater than register right. This is the same comparison that we want to make. So you see that this test is found here. Another important part that I forgot to mention is that this particular example says that we have 2 signed numbers, and because of that we are looking at this part, okay, this section of the summary. So since we have signed numbers and we want to check if a number is greater than another number, then we have to look at that specific row. This row tells me that I should use this mnemonic. We should use branch if lower than. Be very careful because you also have another mnemonic which is branch if greater. However, this mnemonic, be very careful, it's the opposite. Now we know that we should use branch if lower than. Now let's see the code. So let's start with some definitions. We haven't seen this in other examples, but we can actually name different registers and make them like variables. So we're saying that register 16, we're gonna name register 16 as num1. Okay, so every time we write num1, we're gonna refer it to the same address, and this is very, very important. It doesn't mean that anytime you write number 1, you're gonna have register 16. This is just an alias for the address of register 16. Then we're defining number 2 as the alias for the address of register 17. And then we have another definition, which is abs underscore val, which is equal to register 18. And this is for better understanding the code. So first we make the comparison. Remember that we have a note that says use branch if lower than, however, interchange the operands. Take a close look. This is important. The code says, the pseudocode says if number 1 is greater than number 2. However, if you see the code, we're inverting the operation. That's because we do not have an operation or a mnemonic that checks if a number is greater than another number. However, we do have a mnemonic that checks if a number is less than another number. So you can see this comparison in 2 different ways. Either number 1 is greater than number 2, or you can say number 2 is less than number 1. So this is what we're doing. Since we don't have a greater than, we don't have that mnemonic, we're going to use the less than, but we're going to invert the operation. So we're not going to check if number 1 is greater than number 2. We're actually going to check if number 2 is less than number 1, which is the same, but again, we're inverting the operation. The next instruction is we use branch if lower than, and take a close look. Even if we have branch if lower than, it says number 1 is greater than number 2. Of course, if number 2 is less than number 1, it means that number 1 is greater than number 2. Now we have this piece of code, and this is important. This code will execute if the branch does not jump. So this is actually the else, okay? Because if number 1 is greater than number 2, then we're gonna jump this code. So if we do not jump, this is the else. This means that the number 1 is less or equal than number 2. And the else part says that you want to make sure that you subtract number 1 from number 2, or you perform the operation number 2 minus number 1. So you can see that the subtraction, it's performing number 2 minus number 1. Okay, and then we're making a move because the result is going to be stored in number 2, and we're moving that value to the apps bulk, which is register 18. And now we have the whole code. If we have number 1 being greater than number 2, then we're going to perform this instruction. Then we're going to move number 1 to the absolute value. And of course, then we're going to continue with the whole program. So thanks for watching. Hope you enjoyed the video.